Hi guys, so we will start our lecture today with the third lesson, training loop from scratch. So the goal of this lesson is to understand how neural networks are trained without relying on high-level abstractions such as nn.Module or optimizer. This builds a strong foundation for debugging and interviews. So we are done up to this, yeah. So what is the core training steps? The training of neural network consists of four fundamental steps: forward pass, loss computation, backward pass, and parameter update. All deep learning frameworks automate these steps but do not change them. Yeah. So let us start with a simplest possible model, that is y equals to wx, where w is learnable parameter. And we take a data x value equals to 2 and y true value we have equals to 8. Now what will be the correct value of w, so that wx equals to 8? So it should be 4, yeah, but this is unknown during training. We need to find this by minimizing the loss. So let us start our weight initialization by taking w value equals to 1. Yeah, and why we are writing here requires grade equals to true. As we have studied in our previous lecture, it enables gradient tracking. Means it will enables all the what we say, yeah, all the yeah. So it will tap all the computation involving this w. So at a forward pass, y predict equals to w into x. So this will be the predicted y value, and our initialized w value is equals to 1, and as x equals to 2. So the y predicted will be 2 into 1, 2, but our y true is 8. So it is like we have to update the weight so that it can give 8 as a predicted value. So we will calculate the loss. So what is loss? Loss will be y predicted minus y true whole square. So the loss must be scalar to enable backpropagation, as we have studied in previous lecture why the loss should be scalar. Now in backward pass, what happened? We do loss dot backward, which compute the gradient, which is dou loss by dou w, which is and this gradient value gets stored in w dot grade. Yeah. Now we will do parameter update. Parameter update is done in this way: w equals to w minus eta into d by dw, where eta is learning parameter. So with torch.noGrade, torch.noGrade, w equals to, yeah, so we are taking our loss learning rate as 0.1. So it is this whole equation is actually abstract form of writing w equals to w minus 0.1 into w dot grade. W dot grade, why? Because it stores this value. Yeah. So we are writing it as w dot grade. And with torch dot no grade, why we are writing this? Because it is used to prevent tracking parameters update. Because if we will not write it, it will also be tracking the parameter updates, but we don't want parameters update tracking. So that's why torch.grade is used here, so that it cannot track parameters update. Now gradient reset. After all this, we write w.grade 0, because if we will not do this, it will start accumulating the gradient value, and it will add after every steps, it will add the previous grade value. So it will accumulate all the gradient, but we don't want it. We want isolated gradient for each steps. That's why we do this. Now the key interview takeaways are: learning occurs during the parameter update step. Yeah, backpropagation only compute gradient. Forward pass build a computational graph, and the gradients accumulate unless manually cleared. Now lesson 4, it is manual training with weight and bias. We extend a single parameter model to include the bias terms like y equals to wx plus b. Both w and b are learnable parameters. Now both parameters be PyTorch tensor and having requires grade equals to true. Why we are writing this? Because we want to compute a gradient for both. Now because both are learnable parameters. Now forward pass, what will happen? We will predict y predict will be equals to wx plus b. Now we will calculate the loss as it is, and then we will calculate the loss dot backward. Now loss dot backward will compute two gradients because we have two learnable parameters, so we can know the values of this derivative by writing w dot grade for w and b dot grade for this one. Now parameter gradient is the update parameter as similar to previous what we have learned for w for bias. This updates are performed inside torch.nograde because we want to prevent parameters update store tracking. And now after this we have to reset, or we have to make it 0 because we don't want to accumulate the gradient value after each step. Now the key takeaways is bias is a learnable parameter like weight. Yeah, training logic remain unchanged with more parameters. Yes, and manual training reveals what optimizers automate. Now the next lesson is training modules using nn.Module. So objective of this lesson, the goal of this lesson is to understand how PyTorch train model using nn.Module without treating it as black box. The focus is on writing a training step loop by loop. Now the key idea, nn.Module does not change the learning process, it only provides a structured way to do it. Store learnable parameter, define the forward computation, but the code training logic remain the same as previous one. So the firstly we will define our model as y equals to wx plus b. The model is implemented by inheriting from nn.Module. Learnable parameters are defined using nn.Parameter. The forward computation is written inside forward method. So yeah, we will have one example, I guess. It is here full working code, but before this we have to learn, we should know about each component. So there is one line super dot int. So why it is required? Calling super dot int ensure that PyTorch properly register all the parameters like weight and bias, and the model integrates with autograde and optimizers. Autograde and optimizers are important for training process. We will know it later. Through I will explain it through the code. Without this call, parameters will not be tracked correctly, as we have to track the parameters so that we can find the gradient. So without this, the parameter will not be tracked. We know about mean squared, the same. Now there is another concept of optimizer. So a stochastic gradient descent is used to update parameters. The optimizer performs two key operation: optimizer dot step update parameters using gradient, and optimizer dot zero grades clear accumulated gradient. Now you don't need to write loss dot backward, but just you have to write these two lines and it will do all the tasks automatically. Now here optimizer sorry, you have to write loss dot backward. Like after that loss dot backward you don't need to do this step. W equals to w minus theta times gradient. Just writing optimizer dot step will update the parameter, and optimizer dot zero grade will reset the gradient. And there is also topic called early stopping. We will learn it further in our course in very deep. Early stopping is implemented by checking the scalar loss values. We like if the loss value decreased by after every iteration, we don't want to make this training like take so much of time, and if loss is not improving or it is behind some threshold value, we stop the training because it's already had been trained. Why to make the model more complex or learn the data? So we stop it early. Learning happens during the optimizing steps, not during backpropagation. Yeah, because during optimization step only we are updating the parameter. Backward pass computes gradient but does not update parameter. Yes, as in backward pass we only compute gradient, but we not update parameters. Gradients accumulate by default and must be gradient accumulate by default and must be. Wait a minute. Yeah. Hmm. So parameter update happened after. Uh, yeah, gradient accumulate by default and must be reset every iteration. And nn.Module provides structure, not magic. Yeah. So here, interview takeaways is the PyTorch training loop always follows the same pattern. nn.Module organize parameter and forward logic. Optimizer automate parameters update. Yeah, we will learn this all through one example. I will show you after this. This is the core training idea. Now, here is one example. Complete working code. What we do, first of all, we import torch and we import torch.nn as nn so that we can use directly nn in spite of calling torch.nn. So, firstly, we will define the model. We are defining a linear model with by giving an argument nn.Module because we have to do all this through nn this torch.nn library. So we will, yeah, so this nn.Module organize parameter and forward logic. So it will organize all the parameters and this forward logic. That's why we are giving it as argument here. Now we will define first super int why we are doing to register all the parameters that we have studied why we are writing this line. Self.w, so w is our weight which is a parameter and its initial value is 5, and then again the second value is b, that is bias, and its parameter it is also parameter because it will be also be getting updated, and its initial value is 1. And the what this is the forward pass logic w into x plus p. Now we will create a model instance by calling linear model, as it is a linear model, storing it in a model. So we have called this and stored it in model. Now we will start with our input, which is 2, and our true y true value is 30. Now if we will follow this logic, what will be the initial y value? It will be 5 into 2, 10 plus 1, 11. So it is 11, but our original y value is 30. So we need to update w and b. Now we will call loss as like this. We don't have to do it manually. Just call, because nn have all this method. So just call nn.msc loss and give it like store it into criterion variable. So it will be stored here. Now we need to call optimizer which will update the parameters. So we will be calling it as torch.optim.sgd. So stochastic gradient descent, we write it as sgd. We will call it on model parameters by giving learning rate equals to 0.1. This is eta value which was in that equation w equals to w minus eta into dl by dw. So this is that eta learning rate, and we have to update our model parameters. That's why we are passing it as argument. Now the training loop start. For I equals in range of 100, we will run it like 100 times. So first predicted value will be 11, as we have calculated through this. It will be 11. So the first value is 11. Now we'll calculate the loss because actual value is 30 and our predicted value is 11. So we will give 11 and 30 as a argument, which will be, yeah, this is our that criterion as a loss function. So it will be stored in loss. It will be stored in loss. Now if we want early stopping, like loss is not improving or loss had been beyond threshold, we don't want to like keep it training for a long time. So we check it regularly that if the loss item has been is smaller than this threshold, then we stop it early and break the loop. But if it is greater than this, then this will happen. Loss dot backward will be calculated, and this means that dl by that dw and dl by db will be calculated. Now optimizer dot step will update that w and b value, and after this optimizer dot zero grade will make that dl by dw value equals to 0, so that it cannot accumulate that w dot grade and b dot grade value, which we will not be writing because it all had been abstracted inside because this step do all these things, optimizer dot step, so we don't need to write that w dot grade and b dot grade is stored at values. So and this step will make it 0 so that it cannot get accumulated after every step. And after this we are printing to see how is model getting trained. So nn.Module, what does it do? Stores the parameter and define the forward pass. Yes. Loss.backward computes gradient but does not update weight. Optimizer.step perform learning because it is updating the weight. Optimizer.zero grade prevents gradient accumulation. Yes. The training loop structure is always the same in PyTorch. Yes. Now, interview takeaways is PyTorch training is explicit and controllable, and in modules add structure, not magic, and understanding the loop is very more important than memorizing the API. So we should understand, not memorize the API. If you want, let me. So we will do it in next lecture, 3 lessons. So bye bye. Thank you.